My name is Aisha Hortachsu, and on behalf of the Applied Technology Council, I would like to welcome you to this webinar on improving performance of buildings in very high seismic regions, FEMA P-2343. This webinar is brought to you by the Applied Technology Council under a contract with FEMA, the Federal Emergency Management Agency. If you haven't already, you can download the handouts using the link in the chat. We know that many of you are interested in receiving professional development hours for your attendance today. For those who registered and attend the webinar, a certificate documenting professional development hours will be sent by email within 4 weeks. If at any time during the webinar you have questions, please type them in the Q&A window that you can open from the Zoom control panel. We are planning to have a live question and answer session at the end of the webinar. Please submit your questions as you have them rather than waiting until the end to submit them. We will answer as many questions as we can, time permitting, at the end of the webinar. If there are any questions that we are not able to answer live, we plan to provide written responses for as many as is practically feasible. I would now like to turn it over to Mike Tong from FEMA's Earthquake and Wind Programs branch, who will provide a brief introduction to today's webinar. Mike, please go ahead.
Thank you, Aisha. Hi, everyone. My name is Mike Tong. I'm the FEMA Project Officer, and on behalf of the FEMA National Earthquake Hazard Reduction Program, NEHRB, I'd also like to welcome you to this webinar. Many of you are familiar with NEHRB. FEMA is one of the 4 NEHRB agencies. Our responsibilities in the program emphasize research and practice implementation and building earthquake-resilient communities. FEMA provides practical guidance documents, building code resources, outreach materials. We also support problem-focused studies as an effective way to address critical issues that can largely impact at-risk communities. As Aisha just said, this webinar is about a new FEMA P-2343 report entitled Improving Performance of Buildings in Very High Seismic Regions. This 2-volume report gives details of a problem-focused investigation on elevated building collapse risk in very high seismic regions. FEMA is pleased to support the project and the webinar. The report was just released to the public last week. There are 43 million people and over 13 million buildings in the United States that are located in the regions with this elevated risk. FEMA P-2343 presents the analysis results, findings on this issue, as well as discussion on the root causes. The study reveals a consistent trend of increasing probabilities of collapse at MCE ground motion, the maximum considered earthquake as defined in the National Design Standard ASC 7 and the International Building Code. And the stronger the MCE, the higher the collapse risk. More importantly, this trend is seen across all the investigated structural systems, despite their code compliant and by different materials. The root causes of the issue are complex and found largely due to increased displacement demand exceeding inherently limited displacement capacity. The report also offers some technical recommendations to help reduce the impact of this issue. For those of you not have downloaded the report, a link is provided in the chat so you can download one. I'd like to take this opportunity to send our presenter and the project technical director, Charlie Kircher, and ATC for presenting the webinar, and leading the project. Thanks also go to Project Technical Committee and its work groups, the Project Review Panel, the Technical Advisor, Project Manager, American Institute of Steel Construction, and the U.S. Geological Survey for their devoted efforts, reviews, guidance, management, and contributions. Hope you enjoyed today's webinar. And if you're interested in FEMA NEHRB recent products and activities, please follow us at the FEMA website. Thank you. Now go back to you, Aisha.
Thank you, Mike. Now let me tell you about our presenter today. Charlie Kircher is a principal of Kircher & Associates, where he provides consulting services to a variety of clients that include commercial and industrial businesses, military and government organizations, and other engineering companies. He has more than 40 years of experience in earthquake engineering, focusing on vulnerability assessment, risk analysis, and innovative design solutions. Charlie is active in seismic code development committees of CEOC, ASCE, and BSSC. He is a fellow of CEOC, an honorary member of the northern section of CEOC, a recipient of the ASCE Structural Engineering Institute Walter P. Moore Jr. Award, and was elected to the National Academy of Engineering. Dr. Kircher was the project technical director for the ATC project that led to the publication of the FEMA P-2343 report. I would like to now turn the webinar over to Charlie. Charlie, please go ahead.
Thank you, Aisha. Great introduction. Welcome all to the webinar. I'm going to be providing an overview and summary of the scope, methods, and findings and recommendations of the FEMA 2343 report. It's very comprehensive. It's technically intensive. There's going to be a lot of material that will be summarized, and you're going to want to look into the report for the details that I cannot possibly cover during the presentation. Again, Mike alluded to the project team. Mike and Bob, FEMA reps, are the project sponsors. Applied Technology. Special thanks to Justin Maresco for being the project manager and running HERD. We have an excellent team, both in terms of the project technical committee, the project review panel, and the working group members, which is another way of saying all of the folks that actually did many analyses that make this all possible. In terms of some background on the project, the impetus for this project was a prior related project, the ATC 116 project, which can be found in the FEMA 2139 series of reports. That project looked into a very interesting question about what was causing a paradox, which was a paradox of analyses finding or thinking that there was a higher probability of collapse for short period buildings than practitioners were recognizing or we were seeing in actual earthquakes. So we looked at that. It took us quite a while to figure that one out, but during the process of figuring out what that paradox was and solving it, we did an evaluation of some of the models of that study for higher seismic ground motions, and we found that although we just had a few models that we checked, they systematically showed a higher probability of collapse. That is, when we designed the model or structure for, say, 1.5 times higher forces, we would expect it to have the same collapse performance when we shook it with 1.5 times the higher forces. But no, the probability of collapse went up, and that led into this project, the 154 project, which is documented in the 2343 report, which really investigated what was the cause of that increase. What are the trends? As Mike said, Mike gave a great summary, by the way. What is the root cause and what are the trends? And that, on the prior project, took 7 years to figure it out, and only took us 3 this time. So we're getting better at figuring it out. But the real purpose was to figure out, by investigation of the collapse vulnerability of these buildings in what we call very high seismic regions, what is causing this? Are there consistent trends? Are the trends the same for all the different model building types, all the different types of structures? So with that, I give you the table of contents. We have 2 volumes. In the first volume, we have the main chapters and the primary appendices that support those chapters. I cannot possibly cover all the technical material. I'm going to talk a little bit about our collapse methods and of course, the collapse results and the trends we see. What I'm going to be a little short on is covering some of the details of the numerical modeling that underscores our analyses of wood light frame buildings and non-wood building systems. And I simply, again, refer everybody to look at the document to see all the incredible detail that went into making these models. I'm going to also talk a little bit about, at the very end, about a capacity spectrum method as a tool to better understand the root cause of the trends, and also to generalize those trends to other situations that we could not study in this project. So what are regions of very high seismicity? For this project, they are defined by the level of shaking of the FEMA P-695 document, where the level of shaking is referred to as the seismic design category D max level ground motions. P-695, for those who may not know it, is a technology that is referenced by the code for evaluating the collapse performance of new structures being brought into the code to make sure that the proposed seismic performance factors, such as the R factor, are appropriate. That's the purpose of P-695. We're going to use it to just evaluate collapse. Definition of very high seismic design category D max, and that document is defined by short period ground motions for default site conditions, where the ground motions exceed 1.5 Gs, and at 1 second shaking, where the spectral accelerations exceed 0.9 G. This is a very significant level of shaking. This is not trivial. This is, in effect, what we used to call the old zone 4. So it's a very high seismic, but we're going to look at things that are beyond that boundary. This, as I said, is the highest level of shaking that is used by P-695 to evaluate a new structure. It's based on ASC 705 ground motions. They're now almost 20 years old. And P-695 purposely excludes sites close to faults. And this definition of very high seismic is the same as the deterministic lower limit of the ASCE 7, which has changed substantially since the original inception because the ground motions have become stronger. So performance-based criteria of ASC 722 and prior editions have established a 10% probability, an acceptable target reliability of 10% probability of collapse given MCER ground motions for risk category 2 structures. This is based largely on the P-695 study. And it is also the preferred methodology for determining the parameters, the seismic performance factors of a new system, or for an alternative system that is not already in table 12.2-1. In terms of a picture of these ground motions, we are talking about the shaded area. You can see the 1.5 Gs at short periods and 0.9 at 1 second. For reference, some of the other spectrum, more current ground motions are also plotted. And long story short, today, ground motions have increased in the velocity region, that's mid periods and longer periods, by about a factor of 2. So this very high seismic region, which still remains the standard by which we judge new structures, is much less than many of the ground motions that are now required for a design. Just as a point of reference, in P-695, when we go beyond seismic design category D max ground motions, we refer to them as E. Logically, you go beyond D, you get E. That is somewhat different than the definition in ASC 722, which is not defined in terms of default ground motions, and rather reference site conditions, site class BC, where the 1 second response is greater than 0.75. There's one of the recommendations of this project will be to reconcile these two differences. Seismic design category, site class conditions, typical site class conditions. D, C, CD, and D are by far the most likely site conditions to be encountered out in the real world. Rock, very stiff sites, and very soft sites are not common. So default ground motions are intended to envelope all those common site conditions. And for site class D, that is the site class with the most energy at longer periods, and it tends to govern collapse. In terms of the risk, Mike alluded to this. This is a map prepared by the USGS for us. Thank you, USGS, showing in the red areas where these sites of very high seismicity are located. You can see them along the west coast of the United States, a lot of Alaska, Hawaii, Puerto Rico. Guam is not shown. It's all very high seismic. Also New Madrid and Charleston, and a little bit of dots around in Utah around Salt Lake City. There are, of the 335 million people in the U.S., there's about 125 million buildings, $62+ trillion of replacement value for these facilities, these buildings. That is about 10%. About 10% of total infrastructure is in these very high seismic regions. If we then look, and then I might add, in certain places like Salt Lake City, it's almost 50% of the populated area. So even though it's a small geographical area, it can have a large impact on a local region. If we look into California, looking down the boxes changed on the lower left, California, about 50 million people, 16 million buildings, $9+ trillion worth of replacement value. Approximately 2/3 of California and the West Coast is in these areas that are where the shaking required for code design exceeds that very high seismic boundary that I defined earlier by 1.5 Gs at short periods and 0.9 at 1 second. So quite a bit of the United States is, and particularly the West Coast and some other hotspots are subject to these higher ground motions. So what is our experience with these performance of buildings in these very high seismic ground motions? In the United States, it's really limited, at least in the last 100 years. In the Northridge earthquake, our last really big one, only a relative small amount of the area in the San Fernando, in the hardest hit part of the San Fernando Valley, exceeded the very high seismic regions. So the real test of U.S. construction really hasn't occurred yet. That's the takeaway. We don't really know what's going to happen. It's going to happen, it will, but we don't have experience with it. When we look outside the United States, we have locations where the shaking has been stronger than the very high seismic region, but the construction isn't necessarily representative of U.S. construction. So we get a bit of a dilemma. But looking, sharpening the pencil a bit with Kobe, where 20% of the buildings collapsed within 5 kilometers of fault rupture. This was reported by the AIJ, the Architects Institute of Japan. That's in contrast to 1.2% of the buildings collapsing when they were outside that 5-kilometer region. So you can see the contrast and the importance of these stronger shakings to the collapse performance. The Japanese researchers parsed some of that data out because they have older and newer construction, and their newer wood construction is similar in many ways to our wood construction. And what we see is that if we're talking about heavy damage, that's not collapse, but it's heavy, it's collapse and some additional bad structural damage, about 57% of the older wood buildings in Japan had heavy damage, whereas there was still 16% of the newer wood buildings with this heavy damage. And that finding is consistent with the FEMA 2343 findings. So we have a bit of a sanity check on some of these predictions of higher levels of probability of collapse. We switch now to discussion of our scope and approach to the project. I'm going to go through an overview of collapse methods, and as I do it, I'm going to give you selected results so you get a feel for what we uncovered, and then after which I will move into findings. What was our real motivation here? We wanted to establish the collapse performance trends that are common to all seismic force resisting systems. We didn't know when we started that this was going to be as true as it was found out to be, but that's the purpose. We don't want to be focusing on any one system. We want something that's true for all the systems. We focus on what I call relative rather than absolute risk. Relative means if I were just achieving my 10% collapse objective, how much worse is it? When we make models, they could have any sorts of collapse protection performance at this very high seismic level of shaking. So we wanted to find a way to bring that all into a common ground and be able to compare all the different systems in a consistent manner. We wanted to also look at differences between far field and near field ground motions, because we knew from prior studies that the records from near field ground shaking tended to produce worse collapse performance than those that were what we call far field in the 695 technology. So the question is, what is the additional risk if you're being shaken with ground motions from near field records where they contained often pulses that are more damaging than records that don't contain pulses? And then the third special study that we looked at, our second special study, was to see how risk category 4 designs performed relative to risk category 2, where we have in the code an I factor of 1.5 that increases the strength by 50%. And the intent of that increase is to reduce the nominal 10% collapse probability, acceptable target reliability of risk category 2 structures to 2.5% for risk category 4 structures. And finally, we wanted to look at, but we could not look at, other very important influences such as site conditions and spectrum shape effects. And we were essentially using record sets that represent only one set of site conditions, but we found them to be important because we used this capacity spectrum method approach to come up with some examples to understand the importance of spectrum shape and, in particular, site class on collapse performance. So this is the sort of things we wanted to look into and looked into. With respect to models, the way we approached the problem was to come up with a set of seismic force resisting archetypes and make models and perform analyses of those archetypes. We wanted to select commonly used seismic force resisting systems for the study and have representative heights and configurations of each of those. We spent a great deal of time looking into overstrength. When we started the project, we were convinced that the answer was overstrength, that the reason that the performance was getting worse, if you will, as the level of shaking got stronger, was that the overstrength wasn't keeping up. That is, when we designed for more force, we weren't getting proportionally more overstrength. We believe that because that is the case for the shorter wood buildings of the prior study. We found that wasn't the case, but we did a lot of homework on overstrength. In the process of evaluating a lot of different systems, models, and different levels of design, we came up with a way of using simplified nonlinear models. That is, to be able to perform a lot of analyses. We would like to have performed them all with very detailed three-dimensional models, but it's not practical. So we found a way to reduce, transform sophisticated models into simpler 2D nonlinear models. And as such, we were able to create, instead of performing designs of all the models, we were able to set up a different of strengths whereby we took the hysteretic properties and scaled them up in proportion to representing different levels of design. So we could perform a lot of analyses efficiently. All of these simplified models were based on, the hysteretic properties were based on published research of prior projects. So we wanted to start out with a good anchor point, so we would be able to get the best set of hysteretic properties possible. And to make sure that they were making sense, we would validate our simplified models against the results of the more detailed models. Sounds good. The shortcoming of the process is that we simply do not have a lot of detailed models whereby the models represent very high seismic designs. It's rare. So the process is sound, but we don't yet have enough of these detailed models of the very high seismic designs in very high seismic regions. So here's the set of archetypes we ended up with. We started out with wood, light frame wood, models because we had all that existing homework from the prior 116 project, and quite well hashed out hysteretic properties. And so when it came to a detailed source of models, we had the prior FEMA P116 project, which is the FEMA 2139 series of reports. That study and this study modeled different types of wood structures in the sense of their configuration. We use something just for reference called STR. That's a bare structural frame. That would be a wood building without any non-structural walls, no gypboard, no sheathing. It's not a realistic structure, but it's what you are required to use for design in the code. It's a baseline. But more realistic representations are commercial and multifamily, COM for commercial and multifamily dwelling. Those configurations were based on realistic configurations of wood buildings 1 through 5 stories. When we moved away from wood, we didn't have as rigorously developed set of 3D models, so we were a little bit hampered, but we did what we could. For 3 systems where we did have some data from prior projects, steel buckling restrained brace frames was one of the systems, steel moment frames, special steel moment frames, and reinforced concrete ductile coupled walls, where we had research available from Irvine on VRBFs. There was a recent prior FEMA project that investigated irregularities. They had taken some stack steel models and jazzed them up, and that's the ATC 123 project. So we had some good models to work with there. And in the ductile coupled wall system, we had a very recent study from folks at UCLA where they had done a P695 analysis to essentially get ductile coupled walls into the code with a larger R factor representing the better performance of ductile coupled walls. For all of these systems, we basically used the far field record set. And people might ask, why far field record set if you got a near field problem? And the answer is because all of the prior studies are basically far field records studies. So to link with prior studies, it made sense to use far field records, many of which are totally appropriate for our purposes. But we also wanted to check the near field. So for the multifamily dwelling wood structures, we also evaluated both the far field and near field records to see what the difference would be. This is a summary of all the models just to impress everybody with the number of analyses performed. So the 4 systems turn into be 32 archetypes. Archetypes meaning different configurations and different heights. Those are broken down into 850 plus models, which have different levels of strength in each of the models. Each of those models is then analyzed for a set of records, far field records, that has 44 components. So there's 44 individual components run through the models, and they're run through at different increments. In other words, establish the performance at different levels of shaking to crank up the models through 44 different increments. And when you put all this together, we had something in excess of 1.5 million individual nonlinear analyses. So simplified models allowed us to form this level of analysis, this scope of analysis. Quickly looking at some of the results for our special study of overstrength, and as an example, this is a wood-like frame. These are example curves of overstrength as a function of the level of design. Level of design is SMT, M for MCE, level ground motions, T for the elastic design pair, S for spectral acceleration. The MC spectral acceleration, we know that as the MCE spectral acceleration increases, design increases, the wood walls become larger to handle that, but the non-structural doesn't. So if the little dashed red curve at the bottom is a bare frame structure with just structural walls, and it has the same overstrength of something around maybe 2.4. And the curves above are that system plus the non-structural walls. And as the wood system gets stronger, the relative contribution from the non-structural walls goes down, and that's why the overstrength goes down, the total overstrength goes down as the level of shaking increases. You can see that how important in wood structures the non-structural walls are. They are, in many cases, the dominant contributor to the strength of the building. So this is why we thought initially that overstrength would be the answer, but it turns out that isn't the answer. Here are our overstrength curves developed for some other systems we looked at. On the left is, I think, moment frames, and on the right are ductile coupled walls. Each system will have its own characteristic. Not shown are BRBFs. They were deemed to have the same overstrength at all levels of design because there was no other contributions to the strength. So they have a constant level. You can see on the left, there's a kind of a U-shaped curve where initially there's some reduction in overstrength and then it increases at higher levels, possibly for a variety of reasons, one of which is drift limits influence the strength added to the building. And on the right, the ductile coupled walls are initially they drop off quite a bit in their overstrength and then they become quite stable. Although the numbers are different and they're important, the overstrength tends to be, for these systems, not to change radically from one level of design to another level of design. But it was all incorporated into the analyses. So as a cartoon of the approach, we start out with a very detailed three-dimensional model. That's the structure you see in the upper left there. It is reduced conceptually to a simpler, for wood, to a simpler 2D model with degrees of freedom at each floor. And for the non-wood structures, the models are reduced down to an equivalent single degree of freedom system, a single lollipop. And the transformation requires coming up with nonlinear modal response properties where the displaced shape at the point of incipient collapse is used to make a modal transformation from a multi-degree to a single degree of freedom system. None of this is actually new material. It's the same material you'll find in the commentary to the ASCE 722 chapter on damping. How do we know it works? Well, first thing, we made sure that the pushover or hysteretic or backbone curve, hysteretic behavior, static, is the same for the models. So we made sure that when we made an equivalent single degree of freedom model, it had the same backbone curve as the more sophisticated multi-degree of freedom and the very detailed multi-degree of freedom model. And if that's true, then when we run records through it and calculate the collapse accelerations, we find they're remarkably similar. In fact, in this case, the failure acceleration of the equivalent single degree of freedom model was closer to the complex three-dimensional multi-degree of freedom model than the simpler two-degree multi-degree of freedom model, although the numbers are essentially all the same. They're all about 2 Gs. So we first make sure we got the same hysteretic behavior, same pushover curves, and when we can, we validated against detailed models. Here's a suite of pushover curves, or backbone curves. For the 15-story BRBF archetype models, there's 20 curves here. They go from a very low level of design, low level of strength, representing a low level of design, to a very high level of strength, representing a very high level of design. We didn't know when we started which of these curves we're going to be using yet, because we don't know where it's failing, but we make sure we had a complete suite of different strengths to make models that could cover all the bases we need to have covered. Typically for the non-wood models, we used 2 different characterizations of the backbone curves, depending, in this case, on the orientation of the columns of the model. Turned out that didn't produce answers that were too much different. Just as you can see in the curves, the pushover curves aren't that different. So our workhorse of all this is the P695 technology, except that it's not exactly the 695 technology as it would be used for a new system. So we adapted it for performance evaluation of these existing systems. So we're not interested in quantifying the R factor, we're interested in quantifying collapse performance. One of the key things that we added to the 695 technology is a explicit calculation of the displacements at the point of incipient collapse. That's not currently required in P695 for getting a new system into the code. Then we used a concept that was developed initially in the 116 project, the prior project, of using collapse surfaces to actually put all the data together. The collapse surface is a surface that characterizes the collapse acceleration, median collapse acceleration, as a function of the two key parameters that govern collapse performance. One of them being the strength of the model, and the other one being the displacement at incipient collapse of the model. These are the two key metrics. And we characterized the collapse surface with a smooth line through the raw data, where the raw data were the results of each of the individual models. Our collapse surfaces quickly, the way we would interrogate to get the drift ratio at incipient collapse is shown here. Up in the right-hand side is a set of IDA incremental dynamic analysis results. The blue dots represent the last point, the failure point, if you will, last point before the model collapses. 695 says that we should look at the median acceleration from these blue dots, and we added this other idea that we would look at the median of the displacement at median failure points. But to populate the whole surface and to also characterize what we call non-simulated collapse failure, we can take the same incremental dynamic results and interrogate the median displacement failure at any drift ratio we want. So here's a couple of them at 8%. The 2.5 Gs has dropped to about 2.35 Gs median at 8% drift, and that drops to about 2 Gs of median failure acceleration at 4% drift, which means as we have less drift capacity, we have less, the acceleration at failure drops with less displacement collapsing, less displacement capacity. And these are used to populate the surface. And here is an example surface, smooth surface through the data. Vertical axis, as I mentioned before, is spectral acceleration, median spectral acceleration at collapse. One axis is the strength, pushover at normal, and we use normalized strength. That is the strength divided by the weight of the structure, and then on the other axis is the drift ratio representing the maximum displacement of the story governing collapse. Some example points along the curve. If I were to slice that surface at, say, 10% in this example, I would see a curved line representing the curvature of the surface at 10% drift. The little orange dots that you're looking at here are the actual data from the analysis of this particular wood structure, one of the 4-story commercial wood archetype models. Typically, the surface fits reasonably well through the orange dots. The reason that there's more than one orange dot at a given level of strength is we had 2 or 3 different ways of characterizing the pushover strength of the models, again, all based from the prior study. Generally, we put a line through this. It's interesting to note that this is already telling us part of the answers we're going to be quantifying later, and that is, the question is, if I look at the blue curve, that is the part of the surface, and I'm at 10% drift ratio, and I'm starting out with a design that produces a strength that's 50% of the weight, V max over W is 0.5. I see that my failure acceleration is something on the order of 2.75 Gs. Now, if I were to double the design, make it twice as strong, so now it's good for 100% of its weight, and I interrogate the surface, I find that the failure acceleration is higher, of course, but it's not 2 times higher. It's 4.25 Gs, which is about 1.5 times higher. That is, if I wanted to maintain the same collapse performance, I would have to have a failure acceleration that was twice as high because I doubled the design. So if I need to maintain the same collapse performance, I have to double strength to do that. It's not happening. So this is a clue that we have a systematic trend, and its trend is traceable to the curvature of the surface. In the P695 world, there are a couple very important collapse metrics that we use. One of them is called the adjusted collapse margin ratio. It is the ratio of the failure acceleration to the design acceleration factored by the spectrum shape factor, which accounts for the rareness of the ground motions. We have target spectra, we have records, and the areas that we're analyzing inherently have ground motions at the MCE level that are rare. That is, they are in excess of the median of the magnitude and distance that governs hazard. And that in itself is another subject, but that was thoroughly worked out in the 695 technology, and tables of spectrum shape factors developed. It is essentially to make sure that we don't overestimate the failure acceleration of an inherently nonlinear structure, such that when it yields from its elastic acceleration into a longer period structure, we know that that the spectrum value we are using must be modified to account for the real shape of the ground motions. So spectrum shape factor, ACMR, is the spectrum shape factor times the ratio of failure acceleration to design acceleration. Very important parameter, spectrum shape factor. Then the ACMR is used in the calculation of collapse probabilities. We assume a log normal curve. It's 695 technology. The next important parameter here is the associated scatter in or variability of the median, or uncertainty in the median value. That is something we set up, I'll show in a minute, for this project. Again, illustrating this process of going from collapse data to collapse fragility to probabilities of collapse. The red dots are a plot for a particular model. This is a WoodCom model, specific WoodCom model. The dots show the trend of increasing collapse probability or fraction, failure fraction with amplitude. The median of that one happens to be about 2.3, about 3.5. That is factored by the spectrum shape factor and ratioed to the design acceleration. In this case, I'm using the design acceleration for a site in Los Angeles. And the answer is that the adjusted collapse margin ratio is about 2. And that, if you look down at the curve at the design acceleration of 2.37, you'll see a number, a collapse probability slightly over 10%. So in this case, we're not quite meeting the target reliability of 10%. And it's interesting to note, and this is pretty typical, it's also about where the red dots are showing us. Red dots are steeper because they do not include all the sources of variability that we put into the log normal standard deviation parameter B sub total. The 1.3 comes from existing tables that have been worked out in the 695 technology. They are different at different periods. They're different for different amounts of inelastic response. They are different for the far field and the near field record sets. Typically, we have highly ductile systems, as this one is. So the amount of displacement-based ductility is 8 or more, so we're up there. And the period is short, so it's 133. You could see in the table that if the period was 1.5, it would be a different value of the spectrum shape factor. So a little background there. For this project, we established some guidelines for the values of the log normal standard deviation, where those guidelines were based on recognizing that, of course, value is a function of the drift ratio. The higher the drift ratio, the more uncertain we are about the scatter in the data. Fair. But we also distinguished between wood and non-wood, where we felt the wood models were a little more reliable than the non-wood models. And we distinguished between risk category 2 and risk category 5 because we argued that risk category 4 would be a little more reliable because they have greater scrutiny, hospitals, fire stations, and things like that. Typical numbers are in the 0.5 and 0.6 range. So, collapse trends. we want to take that surface and extract from it a collapse trend at different increments of design and different increments of shaking. And in that process, we need to relate strength to the design, little formula I'm showing you here, also considering the overstrength, and then we can bring in all that information we learned earlier in the study of overstrength. It's a bit tricky to interrogate the surface when overstrength is also a function of demand, but it's doable and was done. Key points, we wanted to incorporate the actual overstrength from our studies. We evaluate collapse at the point of incipient collapse. We let the models tell us when the structure fails. And for the sake of comparing different models with different levels of design, we normalize the demand such that the design parameter SMT is normalized by the design value, the value of SMT at the VHS boundary. That is to say, when SMT equals the acceleration of seismic design category D max. That is that boundary from the curve. So we normalize the horizontal axis to compare designs that were prepared for different levels of MCE ground motions. Here's some raw results. This is finally get to something that's interesting. Probability of collapse. This is the probability of collapse shown as a function of normalized demand for a number of different systems, a number of different wood models. On the left are the bare structural frames. On the right are multifamily dwellings where the bare frame has stucco and drywall added to it. There's a horizontal axis in there at 10%. That's our target reliability. Along that horizontal axis, I've added the actual seismic demands, the MCE seismic demands of various locations of interest by the names. So we can see, for example, on the lower levels of shaking are places like Sacramento and Memphis, and at higher levels of shaking are sites like Santa Rosa and San Bernardino. When the curve crosses, wherever the curves cross, the 10% tells us the level of normalized demand that meets the 10% target reliability. And when we're looking at wood models on the right that are multifamily dwelling models where they're quite strong because of the non-structural, all the curves are crossing the horizontal line at values of normalized demand greater than 1.0, telling us that we can shake stronger and still not reach that 10% target reliability. On the left, we see that if we had a bare wood frame system, we would not be doing so well. We might be okay for the taller ones, but not so much for the short ones. The thing that struck us when we first saw this is that no matter where these curves fell in terms of crossing the 10% threshold or the target reliability, it was amazing that they all had the same systematic trends. They were always increasing monotonically from left to right, and this is the sort of trend that we were trying to quantify when we started. So if I look at the same information, I'm going to look at the other non-wood systems. In this case, I'm looking at the RBFs on the left side. They are I would characterize as optimistic models. They are quite strong and they perform very well. On the right is the ductile coupled walls. They don't do as well. I wouldn't call them pessimistic, but they're less performers. We're not trying to quantify the difference between ductile coupled walls and BRBFs. That's not what we're trying to do. We're trying to see if they have the same trends of increasing collapse risk. But just to think a moment about ductile coupled walls, if we look at the two ductile coupled wall curves that are for 8-story models, that's a gray and a kind of a yellow set of dots, they're just about 10% collapse performance at 1 times the boundary. At the normalized demand of 1, they're just about 10%, which is consistent with the findings of the UCLA study that got these things moved up from a 6 to an R of 8 in the code. The only difference is that we had slightly different assumptions for the beta, the total collapse uncertainty. The fact that the short ones have a higher collapse probability than the taller ones is entirely consistent with the way ductile coupled walls perform. Coupling beams work better when the building gets taller. And in fact, the code doesn't allow ductile coupled walls with an R of 8 to be used when they get below, I think it's 6 stories. And it was for this reason, because when you get a very short coupling of the two walls, you can't really exercise the coupling beams. So the results make sense with respect to prior studies, but the prior studies only looked at normalized demands of 1. The rest of it we're speculating on in terms of what the models are telling us with the trends going up. We did that for all the systems, including special steel frames, moment frames, and that didn't. The results were unhappy for the special moment frames. They weren't, even though they were based on and calibrated with prior studies, they weren't giving happy answers. So we were asked to take a hard look at that system, where we would prepare, and we did, detailed designs. These are designs by practitioners, not hypothetical increases in strength, but designs by practitioners. We couldn't do much. I mean, you can only do this. Takes a lot of time. We did a 9-story model, and we designed it for 3 different levels. High seismic means the boundary. Very high seismic in this case means 2 times the boundary, and ultra high was 3 times the boundary. And analyzed it using the process. Well, the first thing we noticed in these models of this system is that the designs of this system had a lot more strength, and it had a lot more displacement capacity than the prior equivalent single degree of freedom models. And as such, the collapse performance was much different and much better. You're stronger and you have more displacement capacity, you perform better. This can be seen here. This is a summary of results. It's busy, but if you look where the boxes are, you'll see that the red box on the left is showing you the values of overstrength and displacement capacity, comparing the prior single degree of freedom models with the detailed models of this 9-story model. And on the right, you can see the very different collapse probabilities. The takeaway is different values of overstrength and displacement capacity, you get different collapse probabilities. We said, well, that's fine, but what if we went back and anchored our equivalent single degree of freedom models to these detailed models of the 9-story archetype? And that's what you see down below. And after we got our single degree of freedom models to have the same backbone and hysteretic properties as the detailed models, then, which is shown here in the terms of displacement capacity and overstrength, then there was very, very similar collapse probabilities at these 3 levels of shaking. The plot showing the fitting of the pushover curves of the simple models to the curves of the more detailed models. One of the things to note is that both curves in this case, the very high seismic design, which is twice the high seismic design, even though it's designed only for twice as much acceleration, SMT, if you will, it has 3 times as much strength. So that one of the things we noticed is a lot different values and strength. Whether this is true in all cases is hard to say, but in this case, there was much greater overstrength. And it was influenced by drift-based criteria. We see that we get the same answers when we make the models do the same thing. I'm plotting the collapse results, comparing the prior simple single degree of freedom results from up above. You can see that they have a collapse probability of about 10% at normalized demand to 1, and they go up. The more detailed models, which are shown in results, are shown in the 3 brown dots, and then the single degree of freedom models that are based on the sophisticated model properties are shown in green, and they're about the same answers. There is this kind of a kink in there that annoyed me. It's not supposed to be a straight line necessarily, but why is it changed like it does? When we looked into the actual band capacity ratios of the high seismic designs, of the detailed high seismic designs, they had a much higher demand to capacity ratio than the very high and ultra high, meaning they're going to be collapsing sooner. Meanwhile, the very high, as I pointed out before, had 3 times the overstrength instead of 2 times the overstrength. And if we made those adjustments, then I think the 3 dots would have fallen on a curve that was straighter, not necessarily straight. But I'll tell you, at the end, we've concluded that we really need to have detailed archetype designs for the evaluating of the collapse performance of a seismic force resisting system at these higher levels of shaking. For example, for establishing R factors, we can establish trends using models that are not necessarily detailed or based on detailed models, but we cannot, for example, propose a new value of an R factor. So that's our side study for the 9-story steel moment frames. Now let me move into a summary of findings and generic collapse trends, root cause of these collapse trends, and a generalization of the collapse trends. I'll revisit for a second what we're trying to do. We were going to try and find trends common to all seismic force resisting systems. We were going to look at it from a relative versus absolute risk sense. We were going to look at the far field versus near field and the risk category 2 versus risk category 4 designs. And then, as I said, we really couldn't look at site conditions, but we did look at that a bit with collapse spectrum method examples. Generic collapse trends. We wanted to be able to compare all the results together, which meant all the different systems were performing differently. Sometimes they had 10%. Sometimes they hit the 10% target reliability. Sometimes they were much better than that. So how do we bring them all together? We went back to the collapse surface and said, I can use the collapse surface. I can conceptually adjust the value of the R factor such that all the systems achieve the 10% target reliability for risk category 2 design, achieve that target reliability at the VHS boundary. In other words, I can pinch all the curves to have the same performance at that very high seismic boundary. Then I can see how the slopes look together. And to do that, we defined also another term. So instead of looking at ACMR, we looked at a term called the VHS load amplifier, which is the target value of ACMR, the value of ACMR that achieves the target reliability of 10%. That divided by ACMR gives us a measure of how much more strength structure would need to maintain the 10% probability of collapse as the ground motions got stronger. And for that, we have to go back and get values of ACMR from P695. Typically, their numbers around 2, a little bit above, a little bit below, depending on the value of the log normal standard deviation. And here are the results repackaged such that we have adjusted the curves to have the same probability, 10% probability of collapse at the VHS boundary. So you'll see at normalized demand of 1, we have 10% for all the systems. If you look on the left, you'll see results for wood models, and on the right, you'll see results for wood archetypes, and on the right, you'll see results for the non-wood archetypes. And again, the overarching takeaway is that they all have similar trends. All the trends are increasing collapse probabilities as the shaking gets stronger. And then the question is, why is the slope the same or similar, and why is it different? And that's the tricky part. But again, all of them have the same trends. It's true for all systems. The actual performance of any system may not be the same as another system, but when they're all normalized to 10%, they have very, very similar collapse trends. In terms of the load amplifier, the VHS load amplifier, this is a measure on the vertical axis of how much stronger building would have to be to achieve or maintain that 10% probability of collapse. And you can see that it varies, but again, for the different systems, but the trends are all very similar. So summarizing what we see from that, as I said, consistent collapse trends for increasing collapse risk with SMT. We found that for all the seismic force resistant systems. The shorter wood archetypes seem to have, for example, at 2 times the HS boundary, we found that they have would need approximately 1.4 to 1.8 increase in design strength to maintain that 10% target reliability. Somewhat different for the taller non-wood archetypes, although not drastically different, but it would be more like 1.6 to 1.8 to increase in strength to maintain the 10% target reliability. Near field ground motions. This is where we took the multifamily dwelling structures and ran the near field record set through them. And in general, an approximate 1.3 increase in design strength would be required to achieve comparable performance, all else equal. This is in addition to any of the other prior increases. So in fact, if you're in the near field using a near field shaking with pulses, you would be literally having to almost double the strength to maintain that probability at 2 times the shaking level. With respect to the importance factor for RC4 structures, we found that the target reliability of 2.5% is not fully achieved. It would have to be a number, the I factor would have to be a number more like 1.8 to 2. This is a very easy, conceptually easy change to the code, but the question is whether the 2.5% is really sacred or not. So this could be just simply recognizing that target reliability of 2.5% is maybe too restrictive. But this is one of the things that we will be looking at in the code world. Root cause. What is the root cause of these trends? Why do they? It's not overstrength. We thought it was, but it's not overstrength as original thought. So we want to generalize these trends. And one of our inherent problems is that we use a set of records like the far field record set, and it has an inherent spectrum shape to those records, and it's about a site class CD shape. And that is probably the most important thing to influence the slope of that trend line. The trend line is going always up of increasing collapse risk, but what makes the slope steeper or less steep? And the short answer is it's going to be something to do with the spectrum shape and spectrum shape at the periods that control collapse. But clearly, what is the overriding cause of the collapse trends? The root cause of the collapse trends is that our models, and I think this is fairly representative of the real world, our models have a fixed amount of displacement capacity. It's different for different models. It's different for different systems. But that displacement capacity does not increase with design strength. It might drop off a little. It might get a little bigger. But in general, it stays about the same. Meanwhile, the displacement demand increases in proportion to the increase in the shaking. So we have a limited displacement capacity while we were looking at a systematic increase in displacement demand with increase in the shaking, with the increase in the level of shaking. Mike had mentioned this early on. This is the root cause of all of these curves going up, showing an increase in collapse risk. Looking back, it seems so obvious now, but when we first saw those trend lines, very steep trend lines sometimes, we were not clear at all. This took a while to realize it was really a limited displacement capacity. That's the primary cause of the problem, if you will. It's based on the fact that we have very highly nonlinear models. We are looking at high ductility systems. All of them have high ductility. They're not all the same, but they're ductile. And when they're responding when the inelastic response is significant, the effective period has moved way out from the elastic period, and it's out there that things are made different. If we were looking at structures that were linear elastic, for example, the trend would be flat because the model would actually be able to the model would say that as you double the strength, you would double the displacement capacity. There'd be no change in the probability of collapse. So it's the fact that these part of what we see is because the structures are highly nonlinear. And then the last, and this is the more the ones that we couldn't really evaluate with a single set of records, and that the records trends seem to be very much related to the shape of the spectrum, which is of course different for different site classes and other hazard characteristics, as well as the period of the structure, influencing where you are on the spectrum. So we did see some differences. As I said, it's because the displacement at collapse is fairly stable. This is on the plot. These are the same plots in different domains. On the plot is a plot of the drift ratio, median drift ratio at incipient collapse for wood models. This is a 4-story commercial wood model. They decrease somewhat with increase in shaking, but not too much. It's plotted in the right. It's the same data plotted on top of a 2D surface representation of the 2D representation of the collapsed surface. So we see numbers that the displacements at collapse might vary from 8 to say 10%, but not huge for wood. For the non-wood, it was even more stable. Things might change over the shaking levels from say 7 to 8, or really not change much on the right for the BRBFs. It's this stability of the displacement at collapse that is the reason that the trends will always go up, because the displacement demand will always go up and the capacity does not. So what doesn't matter? As I showed you earlier, the wood buildings seem to be a little bit different than the non-wood buildings, but it was only a modest difference. So that really doesn't explain the strong trends. Overstrength is super important for the overall absolute performance, but since the overstrength was fairly constant, at least we assumed it was, there was no effect from overstrength in the trend, in the absolute collapse, not the trend. Architect displacement capacity, again, not much. Very important displacement capacity, but it stayed uniform at different levels of design. And also the hysteretic behavior stayed roughly the same, so it didn't influence when we could look at it.
Charlie, you have about 10 minutes left.
Thank you, Aisha. So people ask, why are we seeing these things all the same, and why do they look like a straight line? They're really not a straight line, but they appear to be smooth trends because we have a smooth collapse surface. We have similar values of the displacement capacity. But what really matters to us is the shape of the spectrum, which is influenced by height. It's influenced by site class. So we wanted to try and generalize the collapse trends. We can't do it with this one set of records, so we look to collapse the capacity spectrum method to generalize it. It's all in Appendix G of the report. It's a surrogate for nonlinear calculation of median response. And the collapse, that process can take a spectrum of any shape, estimate the median collapse point that we would get as the median, hypothetically, median nonlinear analyses. There's several key assumptions that the same as before, that to make this work, and that is we have approximately equal collapse displacement, hysteretic properties, same failure modes, no change in the spectrum shape. What we found was that, amazingly, that the collapse trend is directly related to the frequency content of the MCE ground motions at those response periods that govern peak displacement response at incipient collapse. It's at the effective period that causes the failure, which is typically 2 or 3 times the elastic period. And it's also out at that range that the slope of the spectrum actually tells us whether we have a steeper or a flatter collapse trend. And this was all done in Appendix G, looking at conceptual basis for collapse. We did 3 different examples. I'll show you some from one example. The notional, we did a notional example where we looked at a spectrum that had 3 idealized domains of constant acceleration, velocity, and displacement. If you're in the acceleration domain, there's no flat collapse trend. if you're in the displacement domain, which is seldom the case because it's so far out in long periods, you would have conceptually the steepest curve, and in between, velocity would be something like the square root of 2. We did one with a site class example, which is very revealing. And then we did one where we actually tried to validate the methods against an example, an actual calculation, calculation for the BRBF4A, and we could reasonably duplicate those results. Capacity spectrum methods. This is a bit quick, but capacity spectrum uses the ADRS format, where the pushover backbone curve is converted using those techniques of taking a based on the modal properties of an assumed shape at incipient collapse to convert the backbone curve from roof displacement, pushover curve from roof displacement to base shear to spectral acceleration and spectral placement. So on this curve, you can see a backbone curve. In this case, it's a baseline curve, and it's been normalized. It's been adjusted to be representative of SA versus SD. Capacity curve is based on, in this example, based on a strength that is assumed to achieve the 10% probability of collapse. There is a demand spectrum that is then scaled to intersect at the assumed, or the assumed displacement failure of 8 inches. And that gives us a point A, which is the intersection of demand and capacity, where we're talking about damped demand. We can go back up the damped demand curve to a spectral acceleration at the elastic period. And we can then convert from the elastic period up to little c, which is the 5% equivalent, which is, in fact, an estimate of the collapse acceleration. Using this concept and applying it to 2 pushover curves, where one represents 10% target reliability and the other one represents some amount of shaking that might be the MCE site of interest. So it's the same idea. The demand spectrum is anchored in both cases to a point, first at A, which is where we have the baseline strength, and at B. And B in this example is set to be twice as strong. And then we go over and read the values of acceleration at the elastic period, and the ratio of C over D is not equal to 2. It's based on the shape of the spectrum. And all this can be characterized by nonlinear control points, AB and A prime, and the linear elastic points C and D. And amazingly, with some algebra, the VHS load amplifier can be calculated as the ratio of the increase in strength, which is 2 in this example, factored by the ratio of the accelerations at C, the accelerations at D. Accepting this for a moment, let's look at this from different shapes of spectra. So if we take the case I just showed you, which is for a spectrum which represents site class C, the VHS load amplifier, because C over D is about 75%, is 1.5. But if I go to a site class C with a very different spectrum shape, very much steeper, then the ratio is 88 and the VHS load amplifier is 1.75. If I go to site class D, the ratio is 0.63 and the VHS load amplifier is 1.25. It's interesting that while in site class D, we have to design for more ground motions, but the VHS load amplifier is less because the spectrum is flatter. All of this can be combined and illustrated in a notional collapse trends, as shown on the right. It can be quantitatively, we know that stiffer sites will give us more risk or more a steeper curve, as would taller structures, because we're moving to the different part of the spectrum. On the bottom of this curve in green is the acceleration domain, where there is no increase in risk, collapse probability. At the top, the red shows us if we were in the the bottom is the bottom is the acceleration domain where there's no increase, and the red curve is the displacement domain. In between are all the other possibilities, depending on where we fall on the spectrum. We can, and of course, I'm repeating the assumptions we saw before. amazingly simple formula can characterize all this. And what is interesting is this is all based on the notion that everything has to go through that 10% probability of collapse at 1 times the normalized demand. Real structures may not be that way. In fact, we could say, what if we were a good at 1.5 times the normalized demand, a normalized demand of 1.5? What would happen? We moved all these curves down, and things wouldn't be as the probabilities would all reduce. And likewise, if we could go out to 2, which we saw for that steel moment frame, then all these curves would again move further down. So I think we have a tool to at least understand conceptually what's going on here, and it's based on the shape of the spectrum at the periods that govern collapse. We have a number of recommendations. I won't have time to go through them all. Some of them are easy, some of them are hard. The one in red is, well, we could solve all these problems by fixing the R factor. That's not going to happen anytime soon. But we are exploring the first 2 about adjusting base shears and also maybe adjusting the I factor. With respect to future studies, it's clear that we need to update P695. It's got the ground motions that are 20 years old. And at the same time, we probably want to fix the definition of seismic design category E. And with that, I will wrap up, Aisha.
Thank you, Charlie. Once again, thank you, Charlie and Mike, for participating in this webinar that is about as fresh as it gets. As Mike mentioned, this document was published just last week, and you can download it from the links provided in the chat. And we do want to remind you that they will be available in the FEMA warehouse. It's just, again, because the document is so new, they might not even know what you're asking about if you call right now. But if you give it a couple of weeks, you will be able to receive it in a printed copy as well. So with that, we have about 12 minutes left for questions. And before we dive into that, I'm going to take a moment to summarize a couple important items. For those of you eager to receive your PDH certificate, note they're only provided for those who registered and participated in the live webinar, not the recording. You can expect your certificate within the next 4 weeks. Due to the large volume of participants, please be understanding that we cannot make exceptions to our PDH policy. If anyone has questions they have not submitted yet, please type them in the Q&A window. If we don't have enough time to answer all of them live, and we only have 12 minutes, we will provide answers to as many of them as possible in writing after the webinar. And with that, I will go to the questions. Charlie, thank you for the presentation. One of the first questions that we got was if there will be a subsequent study to incorporate lessons learned from yesterday's Taiwan earthquake.
Well, that'd be great. I think that's a question to FEMA.
Yes, we will take that note.
Yeah. I would just comment there. Actually, the cover of this report is a building that collapses in one of the earthquakes in Taiwan. So clearly, Taiwan is a place where the very high seismic regions also face a similar kind of the risk. So hopefully, what we study here could be also useful for many other places in the world that will face the similar kind of issues or risks.
Thank you, Mike.
Aisha, let me say something I did not mention. I should have mentioned. This is really important. Along the way, while I'm talking about all the problems about increased collapse probabilities in the areas of very high shaking, the stronger levels of shaking, that same curve goes down to the left, and it goes lower and lower and lower to the left. And what it tells us, this is very important, it tells us that at lower levels of shaking, we have inherently less probability of collapse, just as sure as we have inherently higher probabilities at stronger levels of shaking. And it's these lower, and that's again, all because of the displacement demand and the displacement capacity. And it tells us why we haven't seen more collapses in past earthquakes than we have, because many of our earthquakes have not reached the higher levels, and we've been frankly overestimating the consequences at these lower levels. And this will help explain why we haven't seen the level of collapse, and why the 10% to many engineers seems to be too high, because in past earthquakes in the US and particularly in California, we have just not seen these rates of collapse at all. And it's because we have not been challenging the displacement capacity of the structures. I don't know what the answer is yet in Taiwan, but I know so far the casualties are low. And if the casualties are low, we'll be interested to see what the level of shaking is with respect to the capacity, because it might be that although things are bad, they're not as bad as they might have been, and we'll have a chance to do some more benchmarking. So that was my additional 2 cents.
Great, thank you so much. Speaking of international application, or in the national application, you alluded to it a little bit in your conclusions for your next steps, but more specifically, how do you envision the results affecting the seismic loads prescribed in ASC 7 in the future?
Well, that was the first recommendation slide. That was a conceptual list of all the things we could do, and we're going to be constrained. As I said, like the idea of changing all the R factors, or what we used to call fixing the R factor table, that's just a bridge too far. We might be able to put in some requirements that in the very high seismic regions would increase the strength, or at least require maybe perhaps checking to see where we are with respect to performance. But again, if our buildings are actually performing so well, I suspect that we don't need to radically change the design, but we need to acknowledge the fact that as the shaking gets stronger, the probability of collapse will systematically get higher.
On that conceptual path, do you think seismic hazard maps will include values for R and omega in the future?
God, I hope not. That those are hazard maps. And that's the other side of the coin. I hope we can actually simplify our ground motions, keep them clean, so that because the more we muddy them, the more it's harder to figure it out. But that's my personal opinion.
Thank you. We have a couple of questions about the details for detailing. So, do you have any details about the non-structural wall connectivity to the building, and if there are any criteria about joints and connections in the report?
Yes and no. Our wood, or if you're talking about the wood, I think that's the wood question, the light frame wood. The models are very detailed, and they're based on a lot of study of those sort of issues about how the non-structural is connected. Most of that homework was done in the 116 project. We're making use of it. So it's actually in the 2139-2, I believe is the right one. One of those reports from the ATC 116 project is where a lot of that background on the light frame wood and the non-structural components of those systems can be found.
Thank you. We had a question, possibly the answer is the same. Did any tests for light gauge metal studs included in the studies?
No, we didn't test anything, of course. No. So all of that is the work that goes between. This is the development of the archetype design, and the models of the archetype designs based on testing, which is a very important part of that. Most of that homework was done at least for the wood in the prior project, and no, nothing. I don't recall now about the different types of studs. I think we're talking about basically. Well, I better stop there. I'm not sure what we find in there.
Thank you. Was there consideration of improper ductile detailing as another possible root cause?
Well, no. What we're saying is it's all the same. That's a good question, but this is not because of bad detailing. We're assuming the detailing is pretty good, but whatever it is, it's assumed for all those different levels of strength that we develop models at different levels of strength. Then we produce the collapse surface. We interrogate it. We get the trends. It's implicitly assuming the same detailing or the same non-detailing for all the archetype models that are being analyzed. It's not detailing.
Here's a simple one. What software was used for the study?
That's not a simple one. The wood has its own software. First of all, you're asking the wrong guy. The best one to answer that question will be for wood, Professor Pang from Clemson, and you'll find all the details in the ATC 116 series for wood. Then for non-wood, it's the best one to talk to is Jeff Berman from University, Professor Berman from University of Washington. I think it was Open Seas, although when we did our detailed study of the 9-story steel moment frame, I believe we were not Open Seas. I believe we were perhaps SAP, other things.
We have a question about the ground motions on whether the depth of the epicenter would be an influencing factor.
Well, that's certainly a part of the ground motions. What we're finding is that the shape of the spectrum is totally important. We're finding that there's a big difference between records with pulses and not pulses. That's not a new story. The depth, that's a complete subtlety that I don't think we would find matters to anything. It's in the shape only to the degree that that would change the shape of the spectrum. Answer.
Okay. Will torsion affect the accuracy of capacity spectrum method?
Sure. Technically, there's no reason why you couldn't put, if you made a 3D model of the structure that correctly calculated torsion, then you could build that into your simplified models that would also correctly calculate the torsional effects. In the 695 world, in all the studies we've been doing, we have regular structures. So we don't have, on purpose, we are not trying to deal with irregularities or funky shapes, if you will, for plan configurations. So everything is pretty standard that way, and torsion doesn't show up. It could be modeled, it could be analyzed. It's just not something we were looking at. We were looking at trends common to all systems. We were not getting into the details of say, torsion or not torsion.
Let's see. Sorry, there's a lot of new questions coming in, so I have to listen and read at the same time. Does the study consider structural ductility factor effect and for increasing strength, just properties changed or dimension is increased as well? Sorry, I didn't read that very well. Does this...
Try me again. Try that again. Would you ask? Could you ask the question again?
Does the study consider structured ductility factor for
What's
increasing strength?
Factor?
No, I'm not clear. Sorry.
Yeah. But anyway, the models, when we do detailed designs, as we had on the prior project, yeah, the size of, for strength issues, for example, if you were in a braced frame and you were choosing between, a different set of, different increments of sizes of tubes, for example, that definitely influences the strength of the structure. We were not trying to do that. Again, we were trying to say that this strength is changing uniformly up as we're getting to higher levels of design. I think there would be a step function here and there, a lot of step functions. That would be pluses and minuses on the collapse surface. So that I'd say the collapse surface doesn't care on average, but of course there would be differences in the actual data going into developing the collapse surface.
Great. I think that brings us to the end of our time. And again, if there are questions we weren't able to answer live, we will issue a written response to as many questions as possible. So with that, I would like to thank, on behalf of FEMA and Applied Technology Council, I'd like to thank Mike and Charlie for this presentation and thank everyone for joining us today. Please click on the survey link that pops up when you leave. We especially appreciate your input on topics you'd like to see covered in future FEMA webinars. We use this to plan our webinar program. And lastly, expect a follow-up email in the coming days with the links to the recording, handouts, and the survey again. With that, this concludes our webinar. Thank you very much.